everybody. We are in for another treat today, the mean value theorem. So I've got pictured here a couple of graphs. I want to talk about what this means graphically. That'll help us come up with our formulas for the mean value theorem, and we'll look at two types of questions that use the mean value theorem. So the mean value theorem states that if we just have 2 points on a graph, any two points, as long as the graph is continuous and differentiable, meaning it just has a derivative everywhere, this line right here is called the slope, or it's called the secant line, and its slope is the average rate of change. Just the rate of change from one point to another, slope of the secant line, average rate of change. What the mean value theorem states is that for every continuous and differentiable function, here, let's undo that real quick. For every continuous and differentiable function, why is it doing this? Hey, there we go. What we can do is draw at least one more point where the slope of the tangent line will be exactly the same as the slope of that secant line. All right, so you can see on this graph here that the slope of the secant line is mirrored by, or the equivalent to, the slope of the tangent line right here. So it happens on every differentiable graph at least one time. On this graph here, it would happen twice. I'm just going to freehand sketch this one so it goes a little bit quicker. But from this point to this point, that is our secant line. Okay, right here, roughly, the tangent line would have the same slope, and roughly right here. All right, so at least one time, in between these 2 points, the slope of the tangent will equal the slope of the secant. Now, as a formula, that looks like this. Okay, this is our slope of our secant line, the average rate of change. This is our slope of our tangent line, the derivative evaluated at a point. Okay, and what the mean value theorem states is that these two things will be equal at least one time, as long as the function is differentiable. Okay, and C is always going to be in between A and B. So, an example of when we would use this is a question where we're given an equation, f of x, and we're asked to find the values of c, or the values of x, that satisfy the MVT for this function on this interval. So if this is our question here, again, we're going to use this formula for the MVT. The x values are a and b, so this is a, this is b, so I plug them in here. And if these are a and b, then this is just f of 6, f of 0. All right. Our formula says also to take a derivative. So I'm going to take a derivative of f of x and plug that in right here. All right, so again, all I've done, this is our average rate of change, or the slope of our secant line. This is our instantaneous rate of change, the slope of the tangent line. All we have to do is figure out what f of 6 is, what f of 0 is, subtract and simplify, and then solve this equation for x. All right, so f of 6, if I were to plug in 6, I would get 12. Minus, if I plugged in 0 for x, I would get 0. And so this whole fraction simplifies into 12 divided by 6, or 2. And so we end up with 2 equals 2x minus 4. If we add over 4 and divide by 2, we're going to get x equals 3. All right, so this is the point where if we were to actually graph this function, this is the point in between 0 and 6, where the slope of the line connecting those 2 points is the same as the slope of the tangent line right there. Okay, it will not always be exactly in the middle, just was for this one, where it was exactly in between those 2 points. Now, this is more of an FRQ style question. Say we're given x of t usually represents position. Okay, and so we're told x of t is differentiable, and we're given a table of values, so we don't have all the values of x, just some. First question, must x of t equal 14? Second question, must the velocity be 1 over 6 sometime on this interval here? And so I want us to think through which of these is the MVT, and which of these could be used with another theorem like the IVT, the intermediate value theorem. Well, the mean value theorem always is going to work with average rate of change, right? Average rate of change. So we have to have an interval, f of b minus f of a over b minus a. And we have to have either a derivative that we can find or something that is a derivative. So in this question, B is the one actually that's going to use the MVT because it's referencing velocity and we're given position. So the fact that this is a derivative and we have an interval means we're going to use this one. I didn't put an interval on A, but it absolutely could have an interval from 1 to 13. Okay, so it could have the same interval, but it's referencing x of t, which is not the derivative here, so this one's not mean value theorem. Okay, this problem is what we're looking to do. Two values of t are b and a, and so here the bottom is going to be 13 minus 1. The top is going to come from these 2 points then, right? X of 13 and x of 1, which would be 10 minus 8. Now, if we simplified this here, this is going to simplify into 2 over 12, which is 1 over 6. This question is different from the last one because we don't actually have a position function to take a derivative of. But what we know is the average rate of change will equal the instantaneous rate of change, v of t, somewhere, right? So velocity must equal this somewhere on that interval. So our answer here would be yes. Our reason would be because of the MVT. All right. For this question, because these two are the same, this is actually the intermediate value theorem. And here I would just look for at my y coordinates, right? Or I guess x coordinates here. Look at 14, and does that show up? Do I have to cross 14 to get from this one to this one, or here to here, etc.? Well, yes. Either from 4 to 16 or 16 to 10, we have to cross 14 since this function is differentiable and by extension continuous. Okay, so both of these would be yes. This one is the intermediate value theorem. This one, though, is the mean value theorem. All right, so that's it for this. It's just a quick run through. Hope it helps. And as always, stay flawless.